Oh, hello. Today we are doing 12.1, sequences and summation notation. So first we have to know what a sequence is. So very simply, a sequence is a function whose domain is a set of natural numbers, which is the counting numbers. So if we're doing the counting numbers, what number are we going to start with? What number are we going to start with for counting numbers? 1. Okay, so then we have f of 1, f of 2, and this is going to go all the way up to f of n, depending on what your n value is for a given sequence. Now, when we're doing a sequence, we're going to have a different notation. This notation is a sub n, and that's going to be instead of function notation. So for function notation, we're used to f of n, so a sub n is going to be our sequence notation. So when we're referring to terms in a sequence, a sub 1 is the first term, a sub 2 is the second term, and so on and so forth, and up until the nth term, a sub n. So we're going to explain the differences between a function and a sequence, and we're going to include how the domains affect the graph. So the main difference is the domain. For a sequence, the domain, which we just talked about, is the set of natural numbers, which is going to start with the number 1 and increases by 1 up to infinity. So you're going to have 1, 2, 3, 4, all the way up to infinity. But a function is going to include the numbers between the counting numbers in its domain as well. So therefore, the function is going to be modeled graphically with a line or a curve, whereas a sequence will have a graph of unconnected points. So if you're thinking in terms of a function, for instance, you can have a linear function or you can have a linear sequence. So if you had a linear function, your graph might look something like this, whereas if you had a linear sequence, you would have unconnected points. Okay, so this would be a function. This would be a sequence. Okay, the function contains all the points in between. The sequence is just going to contain those counting numbers. So for example 1, we're going to find the first 5 terms and the 150th term of the sequence divided by a sub n equals an minus 2. So very simply, what we're going to do is we're going to substitute, if it says the first 5 terms, the first one I'm going to find is a sub 1. I'm going to substitute 1 into my equation for n. Okay, so my equation was 8n minus 2. I'm finding the first term, so I'm going to substitute in 1. 8 times 1 is 8. 8 minus 2 is going to be 6. So that's going to be my a sub 1. Okay, now let's try 8 sub 2. So for 8 sub 2, I'm plugging 2 into my formula. 8 times 2 will be 16. 16 minus 2 will be 14. Okay, so why don't you go ahead and see if you can finish finding a sub 3, a sub 4, a sub 5. And then you can check to make sure that you get the proper forms. Okay, so the first 2 I showed my work so you could see exactly how they came to be. I understand when you're plugging in numbers like 3, you can do 8 times 3 is 24 minus 2 in your head. So this is perfectly fine if you just have your final answer written here. 32 minus 2 is 30. For 5, 40 minus 2 will be 38. Okay, and then we also have to find the 150th term. So for that, we would simply plug in 150 for n. 8 times 150 minus 2 is going to be 1,198. Okay, good job. The next thing we're going to talk about are effects of negative 1 to the power of n. So for step 1, I want you to find the first 5 terms of the sequence given by a sub n equals 5, negative 1 to the n. So if I'm finding the first 5 terms, I'm going to start by plugging in 1. Okay, so for a sub 1, if I plug in 1 here, negative 1 to the first power is what? Negative 1. So negative 1 times 5 is going to be negative 5. Okay, let's move on to the second term. So if you do negative 1 squared, What is negative 1 squared? Positive 1. So 1 times 5 will be 5. Okay, now we're going to do a sub 3. So negative 1 to the third is negative 1 times 5, negative 5. What do we anticipate a to the fourth is going to be? Positive 5. What do we think a to the fifth is going to be? Negative 5. Okay, so let's see if we can pick out one of the patterns that happens when you have negative 1 to the n. First, if you're raising it to the n power, anytime you have a negative to an odd power, what's the result going to be? Negative 1. Anytime you have negative 1 to an even power, what's the result going to be? Positive 1, right? Anytime it's to an even, you have a negative times a negative, which makes it positive. So for step 2, I'm asking you what effect does that term have on the sequence, and then explain why it occurs. So one thing that's going to happen, which we can see, is the signs are going to alternate between negative and positive. So just like we did up here, the signs alternate. I have a negative, then a positive, a negative, then a positive. This is going to occur because of the properties of exponents. So let's explore that a little bit. An odd exponent is going to produce a negative result for negative 1 to the n, and an even exponent is going to produce a positive result for negative 1 to the n. Okay, so that's why we do have that alternation of signs. Okay, so now for example 2, we're going to write equations for the nth term of a sequence. So find the nth term of a sequence whose first several terms are given. So the nth term of a sequence, that is another way to say that you are going to be writing an equation. Okay, so it says find the nth term of a sequence. So what we need to do is analyze what is happening from one term to the next. So I have 1, 4, 9, 16. Okay, sometimes you're going to notice a pattern in between them. Sometimes you're going to notice a pattern with its term number. So this is a sub 1, this is a sub 2, a sub 3, a sub 4. Do you guys notice anything about those numbers? Yeah, they're perfect squares, aren't they? Okay, so when you're finding a sub 1, you end up plugging 1 into your equation. So your nth term is going to be a sub n equals n squared. Now you have to check this and make sure that it does work. So if I plug in 1, is 1 squared going to be 1? Yep. Is 2 squared going to be 4? Yep. 3 squared 9. 4 squared 16. You do want to check at least the first 3 terms. Can anybody think about why? They're just special properties with 1 and 2, right? Because 2 times 2 is 4, but 2 plus 2 is 4. Okay, 1 times 1 is going to be 1, and when you multiply 1 by anything, you get itself. So those numbers have some special properties, which is why you want to at least make sure you check 3 numbers out. Now for B, one thing you should notice right away is what we just talked about. Look at the signs of the numbers. What's happening to the signs? Yeah, they're alternating. Negative, positive, which means somewhere in my equation, I'm going to have to put negative 1 to the nth power. Okay, now we can look at what the relationship is in the denominators. I have 3, 9, 27, 81. Does anybody know how we could get 3, 9, 27, 81? 3 to the n, yep, because 3 to the first is 3. 9, or 3 to the second is 9. 3 cubed, 3 to the fourth. Okay, so one way that you could write it would be like this. So a sub n equals negative 1 to the nth power over 3 to the n. Because negative 1 to the n is going to do what? change the signs, and then 3n has to go on the bottom because the numbers that are generated by 3 to the n are in the denominator of the fraction. Okay, so if I plug in 1, negative 1 to the first is negative 1, okay, and then 3 to the first is 3, I have negative 1/3. If I plug in 2, negative 1 squared is positive 1, 3 squared is going to be 9. Negative 1 cubed is negative, 3 cubed is going to be 27. Negative 1 to the fourth is going to be positive 1, 3 to the fourth is 81. Now there's other ways that you could write this. For instance, one of the properties is if you have the same variable, you could rewrite that as a fraction, negative 1/3 to the n, so that would work as well. Negative 1/3 to the first is negative 1/3, negative 1/3 to the second is going to be positive 1/9, and so on and so forth. So for these, there are sometimes more than one way to write your final answer. All right, let's look at C. Now for C, you probably notice right away what's happening in the numerator. What's happening? 3, 4, 5, 6, 7, 8. So they're going up by 1. In the bottom, I have 2, 4, 6, 8, 16, 32, 64. Do we recognize the pattern there? Yeah, you keep multiplying by 2. So remember, this is your a sub 1. So if you're plugging in 1, you want to ask yourself how you can get 3. Well, you can just add 2, right? If I plug in 1, 1 plus 2 will be 3. If I plug in 2, 2 plus 2 will be 4. 3 plus 2 will be 5. Now for the denominator, you can start with 2, and then this will just be 2 to the nth, because 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, and then so on and so forth. Okay, so that's a good example of one that you can kind of break up into the numerator and denominator and find what you need for each one of those. All right, and then the next thing we're going to talk about is a recursively defined sequence. So a recursively defined sequence is going to be a sequence whose nth term depends on the terms preceding it. Okay, so if it's recursively defined, you need to have the previous term. Okay, so recursively defined means you need the previous term. The way that we write the notation for the previous term is going to be a sub n minus 1. Because if a sub n is the term, a sub n minus 1 is how you can write the one before it, right? Because if I have 3, what's the one before 3? 2, so I could just subtract 1 from 3, right? So that's where that notation comes from. So for example 3, part A, we're going to find the first 5 terms of the given recursively defined sequence. So when you have a recursively defined sequence, you do need to be given one of your terms, and in most cases it will be a sub 1. So your first term in this sequence is going to be 4, and then let me show you how we can plug that in. So your a sub 1 you've already found because they gave it to you. So a sub 1 is given, that's going to be 4. To find a sub 2, I'm going to plug in 2 for n. And the first one I'm actually going to do step by step. So if I plug in 2 for n, I have a sub 2 minus 1. Really, what is 2 minus 1? 1. So it's always going to be the previous term, so 2 a sub 1 plus 5. Our a sub 1 value is 4, so we're going to substitute that into the equation. So 2 times 9 will be 18, so that will be your a sub 2. So now when we go to a sub 3, what we're going to have is the previous term, so 2 times a sub 2, because that's the previous term to a sub 3, plus 5. So I'm going to plug in the previous term, which is 18, which I got from here. And then I'm going to simplify to 46. Then for the next one, a sub 4, you have to plug in a sub 3, which this is 46 plus 5, and then simplify. And then for a sub 5, I'm going to plug in my a sub 4 plus 5, and then simplify. Okay, so if it's a recursively defined sequence, you will use the previous term in order to get the one before it. Okay, now for part B, it says find the 20th and the 100th term of the recursively defined sequence. And I don't know about you, but I do not want to write out 100 terms just so I can find the 100th sequence. Okay, so I'm going to show you a way that you can do it on your calculator.